Section 2.6 Solving equations involving integers. In this video, we will review the definition of a variable and a solution, and how to produce equivalent equations by adding or subtracting the same amount, how to produce equivalent equations by multiplying or dividing the same amount, combining operations, and requirements for word problem solutions. Recall, see section 1.6, that a variable is a symbol, usually a letter, that stands for a value that varies. If a variable in an equation is replaced by a number and a true statement results, then that number is called the solution of the equation. Example 1. Is negative 6 a solution of the equation 2x plus 5 equals negative 7? Solution. Substitute negative 6 for the variable x in the equation. So the original equation is 2x plus 5 equals negative 7. Substituting negative 6 for x, we get 2 times a negative 6 plus 5 equals negative 7. Then on the left, multiply first. 2 times a negative 6 is negative 12. And on the left, we add negative 12 plus 5 is negative 7. Because the last statement is a true statement, negative 7 equals negative 7, negative 6 is a solution of the equation. Adding or subtracting the same amount. Two equations having the same set of solutions are equivalent. For example, 2x plus 5 equals negative 7 and x equals negative 6 have the same solutions. Therefore, they are equivalent equations. Certain algebraic operations produce equivalent equations. Adding the same quantity to both sides of an equation, if we start with the equation a equals b, then adding c to both sides of the equation produces the equivalent equation a plus c equals b plus c. Subtracting the same quantity from both sides of an equation also produces an equivalent equation. If we start with the equation a equals b, and subtracting c from both sides of the equation produces the equivalent equation a minus c equals b minus c. That is, adding or subtracting the same amount from both sides of an equation will not change the solution of the equation. Example 2. Solve for x. X plus 3 equals negative 7. Solution. To undo the effect of adding 3, subtract 3 from both sides of the equation. So the original equation is x plus 3 equals negative 7. If we subtract 3 from both sides, we get x plus 3 minus 3 equals negative 7 minus 3. If we simplify the left-hand side, the 3's cancel and we're left with x. And then on the right, we'll express the subtraction as adding the opposite, so negative 7 minus 3 becomes a negative 7 plus a negative 3. Then if we simplify, we get x equals negative 10. To check the solution, substitute negative 10 for x in the original equation and simplify. We get negative 10 plus 3 equals negative 7. If we simplify on the left side, negative 10 plus 3 equals a negative 7. Both sides are equal with negative 7 equals negative 7, which is a true statement. Therefore, this confirms that negative 10 is indeed a solution of the equation. Example 3. Solve for x. X minus 8 equals negative 11. Solution. To undo the effect of subtracting 8, add 8 to both sides of the equation. So the original equation is x minus 8 equals negative 11. If we add 8 to both sides, we get x minus 8 plus 8 equals negative 11 plus 8. If we simplify on both sides, the 8's cancel on the left, leaving us with an x, and on the right, negative 11 plus 8 equals negative 3. To check the solution, substitute negative 3 for x in the original equation and simplify. We get negative 3 minus 8 equals negative 11. Simplifying on the left side, we get negative 11 equals negative 11. Since both sides are equal, this confirms that negative 3 is a solution of the equation. Sometimes a bit of simplification is in order before you start the solution process. Example 4. Solve for y. Negative x plus 2 equals y minus a negative 11 times a negative 4. Solution. First, simplify both sides of the equation. So on the left side, negative 8 plus 2 equals negative 6. And on the right side, 11 times a negative 4 would be a negative 44. And if we change the subtraction to adding the opposite, we get y plus 44. So we now have an equation with negative 6 equal to y plus 44. We're solving for y, so we will subtract 44 from both sides. Then the 44's will cancel on the right, and we're left with y equal to negative 6 minus 44. Change the subtraction to addition, so negative 6 minus 44 becomes a negative 6 plus a negative 44. Then adding the two negative integers, we get y equals a negative 50. To check the solution, substitute negative 50 for y in the original equation and simplify. So substituting y equals negative 50, we get negative 8 plus 2 equals negative 50 minus 11 times a negative 4. On the left side, we add negative 8 plus 2 equals negative 6, and on the right side, we'll multiply first. 11 times a negative 4 equals negative 44. We'll express the subtraction on the right is addition, so a minus negative 44 becomes a plus 44. Then negative 50 plus 44 equals negative 6. So we now have negative 6 on the left side and negative 6 on the right side. Since both sides are equal, it confirms that negative 50 is a solution. Multiplying and dividing by the same amount. Adding and subtracting is not the only way to produce an equivalent equation. Multiplying both sides of an equation by the same quantity. If we start with the equation a equals b, then multiplying both sides of the equation by c produces the equivalent equation a times c equals b times c. Or equivalently, the product of a and c equals the product of b and c, provided c is not equal to 0. Dividing both sides of an equation by the same quantity. If we start with the equation a equals b, then dividing both sides of the equation by c produces the equivalent equation a divided by c equals b divided by c, provided c is not equal to 0. Example 5. Solve for x in the equation negative 3x equals 30. Solution. To undo the effect of multiplying by negative 3, divide both sides of the equation by negative 3. Take the original equation. Dividing on the left, we get negative 3 times x divided by negative 3 equals x, and on the right, 30 divided by negative 3 equals negative 10. To check the solution, substitute negative 10 for x in the original equation and simplify. So letting x equal negative 10, we get negative 3 times negative 10 equals 30. Since the resulting equation is a true statement, it confirms that negative 10 is indeed a solution of the original equation. Example 6. Solve for x in the equation x divided by negative 2 equals negative 20. Solution. To undo the effect of dividing by negative 2, multiply both sides of the equation by negative 2. So take the original equation, multiply on both sides by negative 2. On the left, x divided by negative 2 multiplied by negative 2 results in x. And on the right, negative 2 times negative 20 equals 40. To check the solution, substitute 40 for x in the original equation and simplify. Letting x equal 40, we have on the left 40 divided by negative 2 equals negative 20. Since the resulting equation is a true statement, it confirms that 40 is indeed a solution of the original equation. Combining operations. Recall the wrap and unwrap discussion from section 1.6. To wrap a present, we first put the gift wrap paper on, second, put the tape on, and third, put the decorative bow on. To unwrap the gift, we must undo each of these steps in inverse order. 1. Take off the decorative bow. 2. Take off the tape. And 3. Take off the gift wrap. Now imagine a machine that takes this input, then 1 multiplies the input by 2, and second adds 3 to the result. This machine is pictured on the left in figure 2.16. To unwrap the effect of the machine on the left, we need a machine that will undo each of the steps of the first machine, but in inverse order. The unwrapping machine is pictured on the right in figure 2.16. It will first subtract 3 from its input, then divide the result by 2. Note that each of these operations undoes the corresponding operation of the first machine, but in inverse order. For example, drop the integer 7 into the first machine on the left in figure 2.16. First, we double 7, then add 3 to the result. Result is 2 times 7 plus 3 equals 17. Now, to unwrap this result, we drop 17 into the second machine. We first subtract 3, then divide by 2. The result is 17 minus 3 divided by 2 equals 7, the original integer input into the first machine. Now, consider the equation 2x plus 3 equals 7. On the left, order of operations demands that we first multiply x by 2, then add 3. To solve this equation for x, we must undo each of these operations in inverse order. Thus, taking the original equation, we will first subtract 3 from both sides of the equation to get 2x equals 4, then divide both sides of the resulting equation by 2 to get x equals 2. Readers should check the solution in the original equation. Example 7. Solve for x in the equation x divided by 4 minus 3 equals negative 7. Solution. On the left, order of operations demands that we first divide x by 4 and subtract 3. To solve this equation for x, we must undo each of these operations in inverse order. Thus, we will first add 3 to both sides to get x divided by 4 equals negative 4. Then we'll multiply second on both sides by 4 to get on the left x and on the right negative 16. Now we'll check by substituting negative 16 for x in the original equation. So we get negative 16 divided by 4 minus 3 equals negative 4 minus 3, which equals negative 7. Since the resulting equation is a true statement, then negative 16 is indeed a true solution of the equation. Example 8. Solve for t. In the equation, 0 equals 8 minus 2t. Solution. On the right, order of operations demands that we first multiply t by negative 2, then add 8. To solve this equation for t, we must undo each of these operations in inverse order. Thus, we will first subtract 8 from both sides of the original equation to get negative 8 equals negative 2t, then divide by negative 2 on both sides to get 4 equals t. We'll check our solution of 4 by substituting 4 for t in the original equation. So we get, on the right, 8 minus 2 times 4, then 2 times 4 is 8, and 8 minus 8 is 0. Because the last line is a true statement, 4 is indeed a true solution of the original equation. Example 9. Solve for p in the equation negative 12 plus 3 equals negative 8 plus 4 plus p divided by negative solution. Since it is possible to simplify this equation before solving, we will first simplify by combining like terms on each side of the equation. Negative 12 plus 3 on the left is negative 9, and negative 8 plus 4 on the right is negative 4. So now we have a simplified equation that we can solve. On the right, order of operations demands that we first divide p by negative 3, then add negative 4. To solve this equation for p, we must undo each of these operations in inverse order. Thus, we will first add 4 to both sides of the equation. Then on the left, we get negative 5, and on the right, p divided by negative 3. Second, we'll multiply both sides of the resulting equation by negative 3. Then on the left, we get 15, and on the right, p. We'll check this by substituting 15 for p in the original equation. Then we get negative 12 plus 3 equals negative 8 plus 4 plus 15 divided by negative 3. On the left, it's easy to see that negative 12 plus 3 equals negative 9. On the right, we'll work from left to right. Negative 8 plus 4 equals negative 4, and negative 4 plus negative 5 is negative 9. Because the last line is a true statement, 15 is indeed a true solution of the original equation. Notice that when we checked our solution of 15, we used the original unsimplified equation. This is because we want to check every step that we used in solving the applications. Let's look at some applications of equations involving integers. First, we remind readers that a solution of a word problem must incorporate each of the following steps. Requirements for word problem solutions. 1. Set up a variable dictionary. You must let your readers know what each variable in your problem represents. This can be accomplished in a number of ways. You can use statements such as let p represent the perimeter of the rectangle, or labeling unknown values with variables in a table, or you can use labeling of unknown quantities in a sketch or diagram. 2. Set up an equation. Every solution to a word problem must include a carefully crafted equation that accurately describes the constraints in the problem statement. 3. Solve the equation. You must always solve the equation set up in the previous step. 4. Answer the question. This step is easily overlooked. For example, the problem might ask for Jane's age, but your equation solution gives the age of Jane's sister Liz. Make sure you answer the original question asked in the problem. Your solution should be written in a sentence with appropriate units. 5. Look back. It's important to note that this step does not imply that you should simply check your solution in your equation. After all, it's possible that your equation incorrectly models the problem's situation, so you could have a valid solution to an incorrect equation. The important question is, does your answer make sense based on the words in the original problem statement? Example 10. A student's bank account is overdrawn. After making a deposit of $120, he finds that his account is still overdrawn by an amount of $75. What was the balance before he made his deposit? Solution. In our solution, we address each step of the requirements for word problem solutions. 1. Set up a variable dictionary. In this case, the unknown is the original balance in the student's account. Let B represent this original balance. 2. Set up an equation. A positive integer represents a healthy balance, while a negative number represents an account that is overdrawn. After the student's deposit, the account is still overdrawn by $75. We will say that this balance is negative $75. Thus, the original balance B plus the student's deposit of $120 equals the current balance of negative $75. 3. Solve the equation. To undo the addition, subtract 120 from both sides of the equation. So on the left we get B, and on the right we get negative 195. 4. Answer the question. This original balance was overdrawn to the tune of $195. 5. Look back. If the original balance was overdrawn by $195, and we let negative $195 represent this balance, the student makes a deposit of $120, add this to the original balance to get negative $195 plus $120 equals negative $75, the correct current balance. Example 11. 3 more than twice a certain number is negative 11. Find the unknown number. Solution. In our solution, we address each step of the requirements for word problem solutions. Set up a variable dictionary first. Let x represent the unknown number. Set up an equation. 3 more than twice a certain number becomes 3 plus 2x equals negative 11. 3. Solve the equation. On the left, order of operations requires that we first multiply x by 2, then add 3. To solve this equation for x, we must undo each of these operations in inverse order. So taking the original equation, first we will subtract 3 from both sides of the equation to get 2x equals negative 14. Then second, we'll divide both sides by 2 to get x equals negative 7. 4. Answer the question. The unknown number is negative 7. 5. Look back. Does the answer satisfy the problem constraints? 3 more than twice negative 7 is 3 more than negative 14 or negative 11, so the solution is correct.